How is it going, everybody? This section we're going to talk about limits. So let's get started. So it says for a function to be continuous at a point, the function must exist at the point, and any small change in x produces only a small change in f of x. A function is said to be continuous on an interval if it is continuous at each point in the interval. All right, so, basically, in other words, the function, it has to be defined at that point, or all the points on an interval. If you're talking specifically about a point, or if you're talking about over an entire interval. So, and I'm going to talk more about the continuity stuff as we work through some examples. So let's look at some examples. So it says discuss if the functions are continuous. All right, so one thing that we can do, like with 1 and 2, is, obviously for number 1, we know that's continuous. It's a quadratic function. Quadratic functions, they're continuous everywhere. They're continuous from negative infinity to positive infinity. However, this function, number 2 here, f of x equals 1 over x minus 2, that's not continuous at x equal 2. Because what happens if we plug 2 in for x? We get 1 over 0. And what happens when we get 0 in the denominator? Well, that's undefined. So let's just look at the graphs of each one. So the graph of the first one, f of x equals 3x squared, well, that's just a parabola, right? There's no holes or jumps or breaks in the graph or anything like that. So it's continuous. Now let's look at the graph of f of x equals 1 over x minus 2. Now, I understand you may not know what the graph of this is, or what the graph looks like. So there's x equal 2, and we have a vertical asymptote here. And so the graph looks something like this. I'm just kind of sketching it in. And you can see it's not continuous at 2. As x gets closer to this number 2, well, what does it do? Well, look, if we're coming in from the left-hand side of 2, what's the y values doing? They're getting smaller and smaller. They're going to negative infinity. And what happens is we come into 2 from the right-hand side? Well, the y values are getting larger and larger. They're going to positive infinity. And what I just said there, as x is coming into 2 from the left, x coming into 2 from the right, I'm talking about the x values are approaching 2. And as the x values are approaching 2, well, coming in from the left, it's going to negative infinity. Coming in from the right, it's going to positive infinity. And that's the concept of limits. As x is approaching a number, what are the y values doing? And we're going to talk more about that. We're going to work several examples involving limits and all that good stuff. All right, so let's continue on. And here it says discuss the continuity of the following graphs. All right, well, let's look at this. We have a graph here, and you see the solid circle right here at x equal 1. Well, this graph is continuous at x equal 1. Okay, it's continuous there. And it's continuous at all the values larger than 1 and at 1. Okay? Now, what about this graph? This graph it's going down forever. It's going down here forever. And you can see the x values, it's continuous on all the x values here, all the x values here. But is it continuous right in here at where x is equal to 1? Well, it's not continuous at 1. Now, keep in mind this function it's not continuous at 1, but it is defined at x equal 1. Because if we plug in x equal 1 to this function, what do we get for a y value? 1, 2, 3, 4. We get 5 as a y value. See, that's a solid circle. This is an open circle. Okay, remember the difference. A solid circle means that's included in the graph. An open circle means there's a hole in the graph. It's not continuous at that hole in the graph. So, and plus you can see that there's a big jump. You see the jump right here? So it's not continuous at x equal 1. And what about this graph right here? Well, there's an open circle. You see the open circle? Well, this function's not defined, in this case 1, 2, it's not defined at -2. So it's not defined at -2, it's not continuous here at -2. But also keep in mind, just because it's defined at a number, okay? Well, let me say that again. It's not continuous here, and it's not defined here, okay? But note over here on this one, it's not continuous at 1, but it is defined at 1, okay? So that can happen. And just to let you know, the graph of the function in number 2, that's this function right here, is this graph, is this function right here. F of x is equal to x plus 2 for x less than 1, okay? And I guess I didn't really draw that very good, did I? That should be coming through here like this, okay? And then for x greater than or equal to 1, it's this graph, and you can see there's a big jump right there. But yeah, that's what this graph, that's the function for it right there. It's a piecewise function, okay? All right, so what does the graph of this function here, what does it look like? Do you know how to graph this thing? Well, let's graph it real quick. All right. So let's see. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, so let's start out graphing this one. So 2x minus 1. All right. So this graph here has a y-intercept at -1, okay? And then we've got rise over run. The slope is what? The slope is 2 over 1, so we go up 2 to the right 1. So 1, 2, and to the right 1. So we're right here, okay? Now, let's evaluate this function at f of 2. So that's 2 times 2 minus 1 is 3. So the point 2, so the point 2, 3, okay, is going to look like this. And I actually have a whole video on graphing piecewise functions. I'm not going to get into the details on it in this video, but if you need to look up on how to graph piecewise functions, just search my channel for graphing piecewise functions, and you'll see it. All right, so the next thing I want to do is let's look at this one. So this has a y-intercept at 5. You see that? It has a y-intercept at 5, but notice to get that 5, that y-intercept, that would be a point, the point right here. You see that? If we were graphing the entire line. But we can't use this point. You see that? We can't use this point, and why not? Well, because that's at an x value of 0, and this is only for x values greater than 2. Okay? So we can't graph the function with the y-intercept. But what we can do is we can do f of 2 is equal to negative 2 plus 5, which is 3. So that means the point 2, 3. But then you might be thinking, well, you can't use 2 because if x equal 2, it goes into this function. And that's correct. But look, we're going to choose x equal 2. And what this is, this 2, 3, this point 2, 3 that we get from plugging it into this negative x plus 5, what we do here is we put you can put like a half circle. And then this graph from this, we put in 2. Now let's put in 3. So what happens when we put in 3? So f of 3 is equal to negative 3 plus 5, which equals 2. So that's the point 3, 2, which is right there. So this graph is coming like this. Okay. Now, keep in mind, I've got this half circle here. That means this graph goes up to 3. It goes up to that point 2, 3, but it's not including that point 2, 3. Okay. And like I said, I'm not going to get in deep on graphing these piecewise functions in this video. Check out the video on my channel if you want to learn more about that. Okay. All right. And we can see that this function is continuous. It's a continuous function. It's continuous at x equal 2. And we can see that from the graph. But I'm going to come back to this problem later on in the video, and we're going to show that it's continuous by satisfying 3 conditions. There's 3 conditions we've got to satisfy for it to be continuous at a x value. Okay? And I'm going to show you how to do that later on. We've got to learn how to take limits before we can do that. But we'll come back to this video and do that. All right. So let's look at this. It says, consider the behavior of f of x equals 2x plus 1 as x. Now, what does this arrow mean here? Well, as x approaches 2. Okay? As x approaches 2, they want to know, what are the y values doing? As the x values get closer to 2, what are the y values getting closer and closer to? So the way I'm going to do this problem, and let me say this, you're not going to find limits like this. You're not going to do limits by using a table. That's what I'm going to do with this problem. The table, it works on this problem. The table does not work on all problems, okay? But I'm just using this table to get you an idea of what we're doing with limits, okay? That's all I'm doing. And the table just so happens to work on this one. All right, so I've got some x values here, and I've got some f of x values. All right, and so what I want to do is I want to choose some x values. So I'm going to choose 1, how about 1.5, 1.9, 1.99, and how about 1.999? And I'll explain this a little more in just a second. And then I've got x, I've got f of x. All right, and I'm going to choose 3, 2.5, 2.1, 2.01, and 2.001. So what did I do here? Well, look at this. If you use a number line, and let's say we've got the number 2 here. So what I did is I started over here at 1, and I just came in closer and closer to 2 from the left-hand side. See, 1, 1.5, 1.9, 1.99, and so on. And for this one, I chose values. I started over here at 3, and I moved in closer to 2 from the right-hand side. 3, 2.5, 2.1, 2.01, and so on. So what I'm doing is I'm getting closer and closer to 2 from the left and from the right. Okay? All right, so what I want to do now is I want to take each one of these x values and plug them in. So if I plug the 1 in, 2 times 1 is 2, plus 1 is 3. And I'm going to do that for each number, okay, for each value. So this one I would get 4, 4.8, 4.98, and 4.998. And then I'm going to plug each one of these values in for x. So I get 7, 6, 5.2, 5.02, and 5.002. All right. Now, let's look at this. As I'm coming into 2 from the left-hand side, look what my y values are doing. Do you see how these y values, they're getting closer and closer to the number 5? And as I'm coming in from the right-hand side, as I'm coming into 2 from the right-hand side, look at my y values. They're getting closer and closer to the number 5. So I could say let's just say it like this. Let's say f of x approaches 5 as x approaches 2. And that's all they're wanting us to do. They want to know what's the function doing as x gets closer and closer to the number 2. Okay? And this is the idea of a limit. What is y approaching, y or f of x, however it's written, okay? But basically, what is the function getting closer and closer to as x is getting closer and closer to some number? Okay? All right, so let's look at this. It says the limit of a function f of x is that value which the function approaches as x approaches the given value a. This is written as, and yes, I write it messy, but this is limit. This is LIM. It would look the limit as x approaches a. The LIM, I just always write it like this. Okay? So the limit is written like this. The limit of f of x as x approaches a is equal to some number L. All right? Where L is the value of the limit of the function. All right, so note, x gets closer and closer to a. X is approaching a, but x may not equal a. Okay, so keep that in mind. X does not equal a. It's just getting closer and closer to a. And then if f of x is continuous at x equal a, okay, so if it's continuous at x equal a, then the limit as x approaches a equals f of a. Wow. Now that's nice. What exactly does that mean? Well, it's saying if your function is continuous at the x value, then in order to evaluate the limit, all you got to do is plug x into the function, and that gives you the limit. Okay? And here we have a function f of x is continuous at x equal a if all three of the following conditions are satisfied. F of a exists, so the function's defined at a. The limit of f of x as x approaches a exists, the limit exists. And we're going to do some examples of some limits that do not exist. And after I work these examples of limits, we're going to go back to that piecewise function, and we're going to satisfy these three conditions. And then and then the third condition, the limit of f of x as x approaches a, has to equal f of a. All right. All right. So let's work some problems. All right. So find the limit, and I've got several examples here. All right. So the limit of x squared minus 7 as x approaches 4. Okay. Well, look, when you're doing limits, just plug the number in. Okay. Is that always going to work? No, but try it first. Okay. So we get 4 squared minus 7, which is 16 minus 7, which is 9. And there's your limit. All right. That's the limit to the function. All right, let's look at this one. All right, plug the 2 in. Now, if you're taking notes, following along with me, don't write this down just yet. So that's 2 times 2 squared minus 3 times 2 minus 2 over 2 minus 2, which equals, that's what? That's 4, 8. Let's see, 4 times 2 minus 6. Oh, so that's 8 minus 6 is 2 minus 2 is 0 over 0. All right, so let's talk about this for just a second, getting 0 over 0. So what do I do? What do I do when I get 0 over 0? Now, I hope if you're watching this video and you're in calculus, I hope you understand that 0 over 0 is not 1. Okay? Don't think of it as 5 over 5 or 7 over 7. 0 over 0 is not 1. All right. So if you plug your numbers in and you get 0 over 0, try something else. Okay? Just try something else. So let's see what we can do. All right. So this is the limit as x goes to 2. Now, let's look at that numerator. Will that numerator factor? Do you remember how to factor? That's what? 2x, x, and that's going to be what? 2, 1, minus, plus, over x minus 2. All right, so all we did, we factored the numerator. And look at that. Those x minus 2's cancel, so I'm left with the limit as x goes to 2 of 2x plus 1. And now I can just plug the 2 in. 2 times 2 plus 1, and that equals 5. And there's my limit. All right. Let's try this one. Plug the 2 in. 2 squared is 4. 4 minus 4 is 0. 2 minus 2 is 0. I get 0 over 0. So try something else. Well, let's look at this. I can factor it. And look at that. The x minus 2's cancel. So I'm left with the limit as x goes to 2 of x plus 2. And now I can plug the 2 in. So I get 2 plus 2 is 4. All right. Let me move this up some. Make sure I got enough room. All right. So let's look at this one. If I plug the 2 in, I get 1 over 0. Now, this is different than when we plugged in and we got what? We got 0 over 0. That's different. If you get 0 over 0, try doing something else. Okay? Here we get a number over 0. We get 0 in the denominator. Now, you know, the first thing you're going to think of, well, it does not exist. And actually, that is the correct answer. But let's understand it better. Okay? Let's understand this better. So, do you remember in the problem where we did the table? We came in to the number, to this 2 here. And actually, well, no, never mind. It's actually the one we're showing the derivative of is actually this 1 over x minus 2. We can see there's no limit there. It's not continuous at 2. There's no limit. But remember in this table here, the x values, we came in from the left and we came in from the right. Okay? And note, and the other thing to notice is as we're coming into x from the left-hand side, it's approaching 5. As we're coming into x from the right-hand side, it's approaching 5 also. So the limit from the left and the limit from the right, they were the same. And if those two limits are the same, then that's your limit. So let's go with that on this problem. Let's find the limit as x approaches 2, and I'm putting a little plus sign there. I'm approaching 2 from the right-hand side. Okay? The limit as x approaches 2 from the right-hand side of 1 over x minus 2. All right, so let's go through this right here. And what I'm fixing to write down is when I write stuff in this color right here, see it's kind of like a grayish color, that it's not really showing my work. It's the process of what's going on in my head, of how I'm looking at this. Okay, so you're kind of thinking this out. So if we take 2, we're approaching 2. Okay, and so I'm going to plug in numbers like 2.1, 2.01, 2.001, and so on. I'm getting closer and closer to 2 from the right-hand side. Okay? So what happens if I plug in 2.1? I get 1 over 2.1 minus 2, so that's 1 over 0.1. What if I plug in 2.01? I get 1 over 0.01. And what if I plug in the 2.001? I get 1 over 0.001. You see that? And look, what is this? This is 10. This is 100. This is 1,000. And what do you think's going to happen is I'm going to get closer and closer to 2. If I add another 0 here, move that 1 over a spot and add another 0. Well, I'll get what? I'll get another 0. I'll get 10,000. And then 100,000, then 1,000,000, and so on. You see that? As I'm getting closer and closer to 2 from the right-hand side, the fractions are getting larger and larger and larger. And so this thing is going to infinity. And then as I take the limit as x approaches 2 from the left of 1 over x minus 2, well, let's think about this. I'm doing numbers like what? 1.9, 1.99, 1.999, and so on. And what happens if I plug 1.9 in here? I get 1 over negative 0.1, 1 over negative 0.01, 1 over negative 0.001, and so on. So what's happening? Well, it's the same thing up here. The numbers, well, they're getting smaller and smaller because they're negative, but just disregard the negative right now. The fractions, they're getting larger and larger and larger, like 100, 1,000, 10,000, 100,000, 1,000,000, but with a negative in front. So this is going to negative infinity. And do you see how the limit from the left and the limit from the right, they're not the same? We say this limit here does not exist. Okay? Because the limit from the left and the limit from the right are not the same. But also keep in mind, if this limit, the limit as x approaches 2 from the right, is approaching infinity, well, that limit does not exist either. It's increasing without bound. It's getting larger and larger and larger. But a lot of times your teacher, or even when you're working problems, and you'll see that later on in the course when you start graphing, yes, this limit does not exist, but we want to know, okay, it does not exist, but what is it approaching? We want to know it's approaching infinity. We want to know it's approaching negative infinity from the right and the left. Now up here, we can't put that it's approaching infinity or it's approaching negative infinity because it's going in two different directions. So we don't have a choice. We have to put does not exist. But we come down here and show the limit from the left and the right to kind of get an idea, well, what's going on. And remember in the graph up there, remember there's your vertical asymptote at x equal 2. And what that graph look like? This and this, right? See, as we're coming in from the left, it's going to negative infinity. There it is. As we're coming in from the right, it's going to positive infinity. There it is right there. And this is important that you can find these things, because later on in the course, what's going to happen is you're going to have to graph stuff like this. And you're going to need to find these vertical asymptotes. And you're going to need to calculate these limits approaching from the left and approaching from the right so you know how to draw the things. Okay? But there it is. It does not exist. That's when you get, you got something over 0. Not 0 over 0. 0 over 0, you want to try something else. But if you don't have 0 over 0, but you have 0 in the denominator, but no 0 in the numerator, well, you need to go about it like this, okay? All right, so now let's talk about this. These are limits, but you notice here on these next 3 examples, these limits, x is approaching infinity or x is approaching negative infinity. Now, as far as these problems go, they work the same, whether it's approaching infinity or if it's approaching negative infinity. You go about it the same way, okay? And I still haven't forgotten about that problem earlier, okay? All right, so let's look at this. So when you have a rational function, see how we've got rational functions here, and x is approaching infinity or x is approaching negative infinity, then I have this right here. This is equal to the limit as x approaches infinity of x squared over 2x squared. Okay? So you might be thinking to yourself, well, what in the world did you do there? What happened to the 1 and the 3? All right, so here's how you think about it. If x is approaching infinity, you have a rational function. You keep the largest exponent from the numerator and the largest exponent from the denominator. Now, what I want you to understand is I am not saying that this is equal to this. I'm not saying that. What am I saying? I'm saying their limits are the same. I'm not saying the functions are the same. I'm saying their limits are the same. All right? Because when you're out there at infinity or you're out there at negative infinity, you keep the largest exponent from the numerator and then nothing else matters. It's meaningless compared to that largest exponent. And then you keep the largest exponent from the denominator. Everything else is meaningless when you're out at infinity or negative infinity. And then, look what happens. See how the x squareds cancel? I get the limit of 1/2 as x goes to infinity. Now, remember this. Make a note of it. Whenever you're taking the limit, no matter what x is approaching, if you're taking the limit of a constant term, your answer is just that constant term, no matter what x is approaching. And so there we get limits 1/2. All right, so let's look at this next one. So this is the limit as x goes to negative infinity. And what do? I keep the largest exponent from the numerator, the largest exponent from the denominator, and everything else goes away. And so I get the limit of 2x. You see that? See, the x squared and the x cubed cancel. I'm left with x in the numerator. All right, so what's x doing? X is going to negative infinity. So I'm plugging in big numbers with a negative sign. So they're really small numbers, right? And so 2 times something at negative infinity, that's going to give me something else at negative infinity. So this is negative infinity. And yeah, look, this limit does not exist, does it? But we want to write negative infinity, or we want to write infinity if it's approaching one of those. We want to know where, okay, it does not exist, but where is it going? Okay. Now, what about this one? This is the limit as x goes to infinity of 5x cubed over x to the 4th. And look there, the x cubed and the x to the 4th cancel, so that's the limit as x goes to infinity of 5 over x. All right, so what's happening here? Well, we got 5 over x, and x is getting larger and larger and larger and larger. So what does that mean the whole fraction's doing? Well, the whole fraction would be getting smaller and smaller, right? And if you don't believe me, get your calculator out and do 5 divided by 10, 5 divided by 100, 5 divided by a million, 5 divided by a billion, and watch what that fraction does. It's getting smaller and smaller and smaller. It's going to 0. Okay? And we got this example, but before we get to this example, I want to go back up here and let's look at these conditions here. All right. So let's go back to that piecewise function and show that it's continuous at x equal 2. So we've got to, f of a has to exist, the limit has to exist, and what else? And the limit has to equal the function evaluated at that point. So let's come back up here and see what happens. Yeah, this is it right here. I'm going to erase this so we can look at the problem. All right, so first condition, f of a has to exist. I want to determine if this thing's continuous at x equal 2. I mean, we know it is, but let's show it. All right, so f of 2 is equal to what? Well, x is 2 up here, so I would plug the 2 into here. So that's 2 times 2 minus 1, which is equal to what? 3. All right. Now, the limit has to exist. So I need the limit as x approaches 2 of f of x, of this function here. Now remember, it's not where x equal 2, it's as x approaches 2. So what am I going to need to do here? I'm going to need to do the limit from the left, and I'm going to need to do the limit from the right to get this limit here. So I've got, let's do this, we'll do it right here. The limit as x approaches 2 from the left of f of x is equal to the limit as x approaches 2 from the left. Now, if I'm coming in from the left-hand side, that means I'm coming in with values less than 2, right? So that means I would plug it into this part of the function. So f of x would be 2x minus 1, which is 2 times 2 minus 1, which equals 3. And then I have to do the limit as x approaches 2 from the right. Okay, so if I'm coming in from the right, that's values that are larger than 2, so that means I'm going to be using this one. So that's the limit as x approaches 2 from the right of negative x plus 5, which is negative 2 plus 5, which equals 3. So the limit from the left, the limit from the right, they both equal 3, so that means that limit equals 3. So I've shown that the limit exists. And now for the third condition, well, look at this. The limit as x approaches 2 of f of x is equal to 3, which is equal to f of 2. See, they're equal to each other. So we've shown that that function is continuous at x equal 2. And that's what it means by showing the three conditions. Right here. See that? It exists, the limit exists, and then they were equal to each other. All right. So I hope all this is making sense. And now, these are videos on this is applied calculus. So let's do a word problem. Now the thing I want to say about a course like this, applied calculus or technical calculus, whatever you want to call it, it's not quite like a full-blown calculus class. The students that take these are the ones that are in like construction technology, like an engineering technology, environmental science, pharmacy students may take it, stuff like that. Okay, and then I don't know what other majors may take it, but there may be some others, but they're not taking all the calculus classes, that the engineering students take. Okay. All right, so let's look at this. It says the efficiency E of an engine is given by E equals 1 minus Q2 over Q1, where Q1 is the heat taken in and Q2 is the heat ejected by the engine. Q1 minus Q2 is the work done by the engine. If, in an engine cycle, Q2 equals 500 kilojoules, determine E as Q1 becomes large without bound. All right, so what we have here is we've got E is equal to 1 minus 500 over Q1. All right, so that they tell us that Q2 is 500. So what would this limit be? Well, that's what we're going to do. We're going to take the limit as Q1 becomes larger and larger and larger without bound. So in other words, what does that mean? Q1 is going to infinity. So all I'm going to do here is I'm going to take the limit of this function here, 1 minus 500 over Q1, as Q1 goes to infinity. All right. And so what I can, and that's Q1 right there. So actually what I can do is I can actually take the limit of each term individually. So this would be the limit. And well, let's look at it like this. I can do the limit individually, but let's just look at it like this. This is just 1, right? So let me ask you this. I mean, I don't know why I'm asking you because you can't answer me, but I'm going to ask you anyway, and you think about it. What is this thing doing? This part of it. Q1 is getting larger and larger, right? So that denominator is getting bigger and bigger and bigger. So do you agree that this whole fraction here is going to 0? And what's the 1 doing? Well, that's taking the limit of a constant term, so it's just that constant term. So this is 1 minus 0, which equals 1. And so that's what E is doing. E is going to 1. E approaches 1 as Q1 approaches infinity. Okay? And so what does that mean? Well, that means the engine is operating, well, E equals 1, so that means it would be operating with 100% efficiency. Okay? All right, so I hope that video helped. I hope it all made sense. I hope you watch some more videos on this. I'm going to do a bunch of applied calculus lectures, post them up. There's some there's students that need these that don't need the lectures like we would do in for engineering students taking those calculus classes. Okay, So that's why I'm doing this. This applied calculus or technical calculus, it's structured a little bit different than the regular calculus. Okay, I mean, you still learn a bunch of stuff, but it doesn't go into the depth like calculus does for engineering students. All right, so check out my other videos. Give me a like, share, and subscribe. Thanks for watching, and I will see y'all in the next one. Later.